Hello, my name is Professor Rad, and this is Precalc video 210, graphing polynomial functions by hand. So this is it, the culmination of all of our work so far. We're going to get to apply it all to graph a polynomial by hand. Now you might be wondering, Professor Rad, this is nice and all, but I have a graphing calculator. Why can't it do that for me? So there are a few reasons that it's important to know how to graph a polynomial function by hand as you move into calculus. So yes, your graphing calculator can graph polynomial functions. However, as we'll see in the next video, knowing some of these theorems and the behavior of the polynomial function is going to help us to better find the correct graphing space. So sometimes when you go to graph a polynomial function on a graphing calculator, your window is not going to be a very good window. So you're not going to get any information. And you want to be able to know where the intercepts are and where the turning points are or might be, and how many there might be to know if you need to look beyond when you do your graphing on your calculator. So you do need to know some of these theorems in this background in order to interpret your calculator results. Also, polynomials are to calculus what integers are to arithmetic. So if I'm going to work with numbers, right, I need a solid foundation on integers or even natural numbers to know how they function and how numbers work and how I can combine them and have a certain developed number sense. So the same thing is going to be true when you get to calculus. Polynomials are your foundational building blocks for that. You're going to see them in every function pretty much. So if we understand how polynomial functions work and behave, then that's going to help us a lot in our calculus class. So in order to get to know these functions, we need to work with them. We need to get messy with them, and we need to graph them by hand so we can understand and have that lived experience with them. So let's meet our polynomial functions by graphing them. And we've got several things to do when you go to graph a polynomial function. Now, I just listed these in an order that kind of makes sense to me. This isn't a definitive order in analyzing or graphing a polynomial function. It's just you want to have some method so that you're accustomed to doing each of these things at some point in your process. So when I go to analyze or graph a polynomial, first, I'm going to find the leading term because it's usually pretty easy to find. Even if I'm in factored form, the leading term is one of the first things I can identify. And that helps me to determine the end behavior, whether it's going to go up on both sides or up on one side, down on the other, or down on both sides. Then I'm going to factor. So when I factor a polynomial, the reason I want it to be in factored form is so that I can easily find the X-intercepts and use the multiplicity to determine what happens at those X-intercepts. I also like to find the Y-intercept. There's only one Y-intercept. I don't know why I made that plural. So I also like to find the Y-intercept so that I have another point to kind of ground me in the graph. So I have the X-intercepts and I have the Y-intercept. Now I'm going to use everything I've determined so far to create a table of signs. The table of signs is going to help me determine where the function is above the x-axis and where it's below the x-axis. And we'll use the multiplicity and the end behavior and the y-intercept to help us identify that. And the potential changes will happen at the x-intercepts because that's where our function is either going to touch the x-axis or it's going to cross the x-axis. So if it crosses, it's going to change signs from positive to negative or negative to positive. And if it touches the x-axis, then the sign stays the same. Once I have a table of signs, I'm going to determine the maximum number of turning points to make sure I don't add in any extra turning points that I shouldn't be adding in. And then I'm going to find any additional points that I think I might need. So if I have two values that are far apart and I'm let me just see what happens in between them so I can get a handle on the scale for my y-axis. And then we sketch. That's all we have to do. So I'm going to write a summarized version of these over here, and then we'll go through an example of applying all of these steps to graphing a polynomial function. All right, so I've got my summary of steps or kind of like a checklist here off on the side. And for this example, we're going to analyze and graph the function f of x equals negative 6x squared plus 21x minus 3x cubed minus 12. So the first thing that we're going to do is we're going to determine the end behavior based off of the leading term of our polynomial. So let's rewrite this polynomial so it's in standard form. So that means our terms have to be in descending order of degree. So that means we're going to start out with negative 3x cubed minus 6x squared plus 21x minus 12. All right, cool. So this means that our leading term is negative 3x cubed. So I'm going to be thinking, since the power is odd, I'm going to think of negative 3x. So negative 3x kind of does something like this. So this means it's going to go up on the left and down on the right. Step one, done. All right, for step two, we need to factor this thing. Now, one of the things that I noticed as I was writing my polynomial up here is that each of these coefficients is divisible by 3. So I'm going to factor out a 3 to make my life easier. And the leading coefficient was negative. So I'm actually going to factor out a negative 3 to begin with. So I get a positive leading coefficient. That just makes my factoring process easier. So that's what I'm going to do. So factoring out a negative 3 is going to give me x cubed. Be careful with my sign changes now. So this will become a plus 2x squared minus 7x plus 4. All right, looking good so far. Next, because it doesn't look like grouping is going to work here, and this is not any special form, I'm going to go ahead and use the rational zeros theorem to find my candidates. Now, if you want to pause the video here and practice your factoring techniques, you can do that and then you can resume and check. Or if you want to walk through a review, I'm just going to walk through it. So to find the candidates, this is that C over L thing, where C are factors of the constant term. So that's going to be 1, 2, or 4. And L are factors of the leading coefficient. So in this case, just 1. So the nice part of this, now that I factored out that negative 3, is that I only have a very few. I'm going to have 6 possible rational roots to test. If I didn't, then I'd have negative 3 as L. So I'd have a 1 and a 3 here. And then I'd have 12. So I'd have 1, 2, 3, 4, 6, and 12. So that would greatly expand my candidates for rational roots. So factoring out that negative 3 did a really good job for us. So I'm just going to check 1 over 1 to begin with. And I'm going to keep checking until I get one that works. So if I substitute in 1, I'm going to get 1 plus 2 minus 7 plus 4. So 1 and 2 make 3, plus 4 is 7, minus 7. Are you excited? I am, because that is 0. The very first candidate, easy one to check, gave us a rational root. So now I'm going to do some synthetic division. So I'm going to throw 1 outside the box and put these coefficients on the inside. So 1, 2, negative 7, and 4. Bring down my 1. 1 times 1 is 1, plus 2 is 3. 3 times 1 is 3, plus negative 7 is negative 4. Negative 4 times 1 is 4, 0. So this is telling me that this is further going to factor into, we've got our negative 3. This 1 means we just factored out x minus 1. And we have x squared plus 3x minus 4. Remember to breathe. So we've got a quadratic. Let's see if this will factor. So in order for this quadratic to factor, I need 2 numbers that multiply to negative 4, but add to positive 3. And if I do a positive 4 and a negative 1, that works. So I'm going to bring my negative 3, x minus 1. And then this will factor into x plus 4, x minus 1. Now, lastly, just to finish this off and make it look nice, I'm going to group my common factors together because I see x minus 1 happens twice. And that's going to be important when we get to multiplicity. So I'm going to rewrite this as negative 3 x minus 1 squared x plus 4. Phew. All right, so I think what I'm going to do is I'm going to erase this work over here, and I'm going to try and keep maybe the left side of this as my like summary of information, and then we'll just keep working on the right here. If I were doing this on paper, of course, I wouldn't erase my work. I'd keep it there so I can use it to reference. So I'm going to write the factored form over here. So f of x is going to equal negative 3x minus 1 squared and x plus 4. So this means my x-intercepts are going to be 1, 0 from this factor. And from this one, we have negative 4, 0. So we factored and we found our x-intercepts. Next, let's find the y-intercept by evaluating the function at 0. So f of 0. This is typically easier to calculate from the standard form because anything with the x is going to vanish and you just get that constant term. So f of 0 is negative 12. So that means we're going to go through the point 0, negative 12. What the y-intercept starts to help me do is it starts to help me figure out a scale for my y-axis. So if I had a y-intercept of 0, 100, I would know my y-axis would have to have a really large scale. Negative 12, not too bad. Next, we want to figure out the multiplicity of each of our roots and identify the behavior that will be happening at each of those turning points. So I'm going to make our little multiplicity table. So we have our root, the multiplicity, and the behavior. So we only have two roots, the 1 and the negative 4. The multiplicity, remember, is the exponent on that root. That's why we wanted to group these two factors together. So the multiplicity on our root of 1 is 2, and on negative 4, it'll be 1. When you have an even multiplicity, that means you're going to have a turning point. So we're going to touch the x-axis, but not cross it. And when you have an odd multiplicity, that means you're going to cross the x-axis. So here we're going to touch, and here we are going to cross. Okay, next we're going to find our table of signs. Now this is something we haven't done yet together as a class. So to make the table of signs, I'm going to use my roots or my x-intercepts as like the splitting up points, because the x-intercepts are the places where my function might turn around or might cross the x-axis. So I'm going to make kind of a little number line, put them in order. So negative 4 and 1, right? So you want it like a number line. Now, I know that when x was 0, we got a y value of negative 12. So in between negative 4 and 1 is where the x value of 0 lives, right? So in between negative 4 and 1, that means the y values have to be negative because we got a negative when we substituted in 0. I know that it's not going to change signs between negative 4 and 1 because of the intermediate value theorem. If it's going to change signs, then it's going to happen at our x-intercept here. Then to figure out what's happening before and after, let's use our behavior to help us out. So I know that I'm going to touch the x-axis at 1. So that means my function is going to come down here, well, kind of come up because we're a negative value. And then we're going to touch the x-axis and then we're going to turn around. So it remains negative after 1. At negative 4, however, it's going to cross. So I had negative values to the right of negative 4, and then I'm going to cross the x-axis and become positive. Now let's use the other information we found to double check this. So we also figured out earlier that this function will go up on the left and down on the right. So that means we should have positive values on the left and negative values on the right. So we can see on the left side of this function, we have positive values, and on the right side of the function, we have negative values. So it'll be going down. All right. And I also, if it helps you to remember that these values came from x-intercepts, sometimes plotting that point helps us to remember that. So there was an x-intercept at -4 and an x-intercept at 1, and then these are the signs, positive or negative, of our function. So that's how we make our table of signs. For the turning points, we're going to do our degree -1. So that means we're going to have a maximum of 2 turning points. So we know one of them is going to happen at this intercept. And then we know at some point between 1 and -4, it's going to have to turn around again so that it can cross there. So we're going to kind of get a natural 2 turning points to this. So to help us, let's start graphing what we know, and then we'll find additional points as we need them. Okay, so we know our x-intercept, so that helps us identify a scale for our x-axis. So we know that we have to go down at least to -4 and up to at least 1. So I'm going to go a couple spaces beyond that. And from the y-intercept, we know we have to go down to at least -12. So I'm going to set something up like this. Four, 1, 2, 4, 5, 6. All right. Remember to label your scale. Now, I'm not going to label my y-axis yet because I only have that one point at -12, and I think I'm going to have to find some more points before I can figure out how to scale this properly. So I'm going to hold off on scaling my y-axis for a minute and just plot those x-intercepts. So I know that I'm going to have the intercept at 1 and -4. So here's an x-intercept at -4. Here's the other one at 1. And I know that we're going to be at -12 somewhere here. I know the function is going to turn around here. Or sorry, it's going to turn around this way. I keep doing that wrong. So I know it's going to turn around this way because we have negative on either side of that turning point. So you're going to turn around like that, cross at 12. And then at some point, I'm going to turn around and come back up. So let's see if we can figure out how far below -12 this function is going to go. So I'm going to evaluate at -2, just because it's halfway between -4 and the y-axis, just to give me an idea. So f of -2, and I'm just going to throw that on my calculator to figure that out. So let's say we've got, I'm going to use the factored form for this. So -3 times -2 minus 1 squared times -2 plus 4. That gave me -54. So I can see that my y values are going to be somewhat large on this axis. So because I now have this point at -54, and I know that this goes through at -12, I think since 6 divides both of those, I'm going to count by 6s. So 6 goes into 54 9 times, so I need at least 9 tick marks to get there. So do 1, 2, 3, 4, 5, 6, 7. Just in case. So let's go to, this is -12, 24. So now I can plot those points that I know. I know at -2, I'm going to be -54. So we're going to go over here. And I know that at 0, I'm going to be -12. Now, depending on how accurate you want your sketch to be, you could sketch from this point on, or you can find a few more points, whatever's going to make it a little bit easier for you to graph. I'm going to find a few more points. I'm going to find what happens at -1 and at -3, just to see if -54 is as low as it's going to go, or if it's going to go a little bit further, just to get an idea of the shape here. So I'm going to go back in and I'm going to substitute in -1. And that gave me -36. So at -1, we're -36. And let's find f of -3. That gives me -48. Okay. So the turning point doesn't necessarily have to happen at -2, but based off of the values we have, I'm probably going to have it turn around maybe just before or even at that point. I'm not going to find any other values for this because I know what my end behavior is going to look like. So I'm just going to indicate that with an arrow. So I'm going to connect these points here. Remember, you want to be smooth and continuous. So no breaks, no sharp corners or cusps. So this value here is my turning point because it touches the x-axis. So I'm going to start out making a little turn there. And we're going to continue. We're going to connect these other points we found. Like so. Then I know I cross the x-axis, so I'm going to become positive after -4. And we turned around here, so I'm going to go negative in that direction. We had a maximum of 2 turning points. So here's 1, 2. So we've satisfied that requirement. And yeah, I think we found, I can put in here, that was -48. So I think we found all the important features of this graph. We made a graph of it, and we can just call it f of x. All right, so with all of our polynomial powers combined, we were able to graph this polynomial function. It is very labor intensive, especially if your function is a pain to factor. But once we get these techniques down, we'll be good to move forward. I will also do a little bit of foreshadowing and mention that this table of signs is also going to be incredibly helpful for solving inequalities that involve polynomials. So you do want to make sure that you're comfortable creating that. So that's going to wrap up graphing a polynomial by hand. In our next video, we're going to graph a polynomial using our graphing calculator. So what the graphing calculator can do that we can't do very easily by hand is it can figure out exactly where this turning point is happening. And it can deal with scales that are much larger and difficult to deal with, by hand. So we'll do an example of that. The graphing calculator we'll be using is the TI-84 Plus, since that is the recommended model for our class. If you have an Inspire, you want to use your calculator manual to help you figure out how to graph. The menus, I think the features are pretty similar, but the menus, the way you access those features are a little different. So at any rate, I hope this helped you graph polynomial functions by hand. I look forward to working with you on graphing with your calculator. In the meantime, we hope you have a magnificent day, and I'll see you soon. Bye.